Hi friends, welcome back. In this session, we will do the hands-on for Betweenness Centrality. As you have learned in our previous videos, how Betweenness Centrality is calculated for both nodes as well as for edges. Using NetworkX library, we will be calculating the node Betweenness Centrality and edge Betweenness Centrality for a sample network now. And for that, we are creating the same sample network that we have seen the manual calculations. So we will use that same example. So let's proceed. And here to start with, I will be importing the NetworkX library. And if you do not have this NetworkX library, as shown in the previous NetworkX basics, you need to first install this package. Then I'll import pandas and matplotlib library as well for visualizing the network. I'm initializing my graph, and this is the sample network that we are creating, which has 5 nodes A, B, C, D, E. And these are the edges that we are defining. It has 6 edges. I'll be creating the 6 edges here. Now, if you want to visualize this particular graph, we will be using plt.figure to create a canvas, and Spring Layout is what I'm using for visualizing this graph. And using Draw NetworkX, we will be coming up with the visualization of the graph. Under the plots, you can see our network. So it basically is giving us this representation. We can automatically change the node size. Say, for example, I will be changing this to 250. Here you can see there is a small red color dot and the node numbers are getting overlapped. So what I'll do, I'll just rerun this code. Now I have changed the node size to 250. It is clearly visible, right? The letters and the nodes are very clearly visible here when I change the size. So appropriately, you might want to make the visualizations. And if you observe, every time I run this visualization, the nodes are randomly, the network is randomly taking the shape here. The alignment. This is because we have not given the coordinates for these nodes. If you want to have a fixed visualization, then you can also define the coordinates for each of these nodes on a 2-dimensional space. Anyways, our focus here is on computing the betweenness centrality. So for node betweenness centrality, we simply call betweenness centrality function from NetworkX library, pass this graph that we have. And this automatically gives us the nodes betweenness centrality computed. And here we can see both node A and node B have the least, same kind of node betweenness centrality, which is less. Whereas node C and node D seem to have the highest betweenness centrality in this network, 0.25. And they are basically at the center, right? The other nodes can be connected when we pass through these nodes. I can sort them. All we have to do is use the sorted function, and I'm trying to arrange them in decreasing order of their node betweenness centrality values. So here you can see node C, node D. They both have the highest betweenness centrality. This is node betweenness centrality. Now coming to the edge betweenness centrality, all you do is add this edge underscore to the node betweenness centrality function. You just say edge underscore betweenness centrality. The syntax, the flow, everything remains same. So this is the edge. 6 edges are there, and we have the node edge betweenness centrality calculated for these 6 edges. We can again arrange them in an order, and we can clearly see that the node, or I should say the edge AC and BD, these two have the high edge betweenness centralities in this network. There will be definitely some difference between the manual calculations and the edge betweenness centrality function that we are using in NetworkX. This is because when we did manual calculations, we just looked at the number of shortest paths that go through this edge when we are trying to find out the shortest paths possible for all the node pairs. So it was more of a count. Whereas in network X library, it computes the normalized value of edge betweenness centrality. So hence there will be slight variations in the calculations.